participants. I welcome you to this very excellent class. Having taken time in our previous class to look at the per unit and what it is all about, its advantage, and how to deal with power systems where we have transformers, how to choose your base voltage, your base power, and how to determine all other quantities having found your base power and your base voltage. Now we want to go into analysis of a circuit. We want to look at how it can be applied in circuit analysis. If we have a circuit, a power system circuit, how can we analyze it? We said the first procedure is like we indicated. You have to choose your base power, you have to choose your base voltage, and ensure that your base voltage will definitely change with respect to each of what the locations where you have transformer. As you meet a transformer, you know that your base voltage is going to change on the other side of the transformer. Then also we now calculate finally our base impedance. We saw in our previous calculation what we did. Your base impedance from this side, and your base impedance would also change as the voltage is changing. The only thing that remains constant is the power, but the base impedance would also be changing as the voltage is changing. And here we are telling you base impedance for different zones, because the transformer tend to divide the circuits into zones. Then we have the fourth one, which will express all quantities in per unit impedances. So of course, as the case may be, if you want, the voltage should be expressed in per unit, the impedance should be expressed in per unit, the current expressed in per unit, depending on what is needed in the circuit analysis. Then we have the fifth point, which is draw the per phase equivalent circuit and solve for per unit quantities. Of course, you can draw the per unit equivalent circuit of the circuit having found all the equivalent values. So now you have all your equivalent impedances or resistances or reactances. So you can now draw the equivalent circuit. From that equivalent circuit, you'll be able to analyze. If, for instance, you have the transformer voltage, you'll be able to calculate the current flowing in the system. If you have the load voltage, you'll be able to calculate the current flowing through the load or through the system, because we are going to see this as we go further in our work. Then we have the 6-point convert back to the actual quantities if needed. Now, like we said, depending on what is needed in the calculation, you have to convert the quantities to their actual value. So let's move in. So power system of this nature, you can see, if you look at this power system, we have look at it here. You can see a transformer, so definitely our voltage will be divided. Meanwhile, let's look at the question. You say the power system consists of one synchronous generator, which is what we have here. This is a generator, and one synchronous motor. Now this is a synchronous motor M. So connected by two transformers and a transmission line. Now this is a transformer T1, transformer T2, and a transmission line. It says create a per phase per unit equivalent circuit of this power system using a base apparent power of 100 MVA and a baseline voltage of the generator G1 of 13 kilovolts. Wow. So we are given a base power. We don't need to crack our head to go and look for the base power. We've already been given the base power. We've already been given the base voltage. Wow. So you see, it makes the calculation, smooth again. We don't need to trouble ourselves. So let's move in now and look at the solution. Now you can see these are the parameters. Now the nameplate parameters for the generator, we have that the power of the generator is 100 MVA. The its voltage is 13.8. So you can see its impedance. So you can see for T1, which is the transformer 1, we have that 100 MVA. We have its voltage. We have this. So for T2, we have that. Now you can see, if you look at here, you see for T1, can you see this is 100 MVA? Can you see the per unit impedance given? Wow, it is actually, we maintain the same, we have the same base power is the same with this, base voltage is the same. So you see we may not have changes here, because if we use that formula, it will just be 1 1 1. They will cancel themselves, so this remains. So but when we look at this, we see, wow, there's a change here. The base power, rather than 100, the base power for this place is 50 MVA. So you can see, so it then means that this reactance, or this impedance per unit impedance, is given to us in this base MVA. There's a change. So you can see even the voltage, there is a change depending on which side we want to use. So in this case, we are also seeing the same thing. There is also a change. There is a change in voltage. You can see we have 13.8. okay, yeah, our voltage still remains 13.8, which is what is here, and you can see all of that. So wow, let us now go into the problem. Now for the line, we have the impedance. Of course, the line will consider the same power, coming into the system is the same power that will go through the line. The voltage of the line will surely be the voltage between this place and this place. So whatever this voltage is, that will be the line voltage. And what is the voltage here when this transforms here, comes here? What is the voltage here? We'll just work with that. So let's move into the problem proper. So wow, now look at this. Let's try to look at it. So we already have that our base power, you can see, is 100 MVA. Our base voltage, yes, in the first region, the given base voltage is 13.8 kilovolts. Now, why are we saying the first region? Let's go back and look at it again. So you see here, you can see our first region. This is region 1, which is where the generator is, and it was given at 13.8 kilovolts. That is the generator. So the voltage from here to here is 13.8. Now, but when we move to this side, this is the secondary part of the transformer. It has transformed the voltage to a value we don't know. That value will be with respect to this turns ratio. So you can see that's T1. That's the turns ratio of T1 now is 13.8 to 1110/1110. So you see that. So we are going to, it then means that the region 2 will have a different voltage. Now when we get to region 3, we can see, look at for region 3, that is T2, it is now moving from 120 to 14.4 kilovolts. So you can see the turns ratio here. So we are going to have a new voltage here. So it then means we have new voltage in region 1, new voltage in region 2, new voltage in region 3. Remember that that is the same way the base impedance will also change. So let's move. So you can see here in region 1 we have is 13.8. So by region 2, because of the transformation ratio, so it transforms this voltage coming in VB1 and moves it straight to 13. We have 13.8 times that, so it has moved to what? 110 kilovolts. Wow, that's beautiful. So this 110 kilovolts comes in into region 3. So when it's coming down to region 3, it's the voltage here. It will be transformed based on this transformation ratio to finally the voltage that should be there. So this will be that is that, and we have 110, which is this voltage multiplied by this. So you see we're going to be having 13.2 kilovolts. So you see that the voltage in region 3 will be different. Okay, like we said in the procedure, we choose the base powers, choose the base voltages, then also calculate the base impedance for the different voltages. So you can see we can get the base impedance. So you can see for region 1 we have that the base impedance is B1 based on the voltage in region 1. This is what is going to be. Look at that. We remember this formula, remember that, and this is what it's going to be. We do the same thing for region 2. When you come down to region 2, the same equation, but here you are going to be using VB2 squared. That is base voltage in region 2 all over base power. We know that the base power remains the same, so that's why we're maintaining 100. So you see 1 to 1. Then for this side you have ZB3, that, and you know this also the same thing. We have the ZB3, we have the voltage in the region 3, which is what we have here, we have there, and we can calculate that. And then now, having calculated the base impedances for each of the regions, fine, can we now go ahead and determine the per unit values of each of the region because we have gotten our base values. Let's now go and determine the per unit values. So now, per unit values of impedances per component in each of the regions. So we start with the first component there, which is the generator. Now, if you look at for the generator, we are saying that since the base power and the base voltages of this particular generator, because we have that the generator power is 100 MVA and the generator voltage is 13.8, so it then means that this per unit value was actually given also in the base values that we actually choose, so we don't need to convert this again to any base. Now let us look at the second part. The second part, we see it holds the same thing from our analysis. You can go and check it. You will see for T1, consider also, you will notice for T1 that the power, the base power for T1 and the base voltage for T1 are still 100 and 13.8 respectively. So it then means we retain the per unit value they gave to us. We are not going to make any adjust it because it was given in our system base. So let's look at region 2. The transmission line we were actually given is actual impedance. You can check from those parameters given where the question is. You see, we're actually given its impedance. So, and its impedance was given to us as the actual impedance as 15 plus J71, and we know that this transmission line is in region 2. So we look at the what is the base impedance for region 2 so that we can convert this actual value down to what the per unit value. So the base impedance in region 2 is 121. So when you divide, when you do this calculation, you are going to arrive at this as the per unit value of what the transmission line. Good. Now, what about the transformer T2? Transformer T2, because after the transmission line, we made the transformer T2. Now, we look at the transformer T2, we notice that there is a difference with transformer T2. Now, look at this. Look at, so we are given impedance of the transformer in a base power of 50 MVA and a base voltage of 14.4 kilovolts. So you can see that these base values, they are different from our chosen system base. So we need to convert the given per unit impedance to our choosing new base or the system base of what 100 MVA and base voltage of what 13.2 kilovolts. Now remember the formula we told you. This is the new base, this is the old base, this is the old voltage, this is the new base voltage, and the rest of that. So when we put that and put all the values that as we're given, we will see now that ZT2, that is impedance of transformer T2 in per unit, will now be equal to the old impedance which we have, which we are given also to be 0.01 plus, that we do that, then this is the old voltage, this is the new voltage. Because we know that in region 3, which is where we have T2 is actually in region 3. Now we are using the secondary side of transformer T2. That's where we want to concentrate. So if we are using the secondary side of transformer T2, is actually in region 3. Yes, so when we do that, we use the secondary side. So what is the voltage at the secondary side? We told you actually the new voltage there based on our system, the choosing system voltage is 13.2, whereas its own voltage is what 14.4, which is the old voltage. So when we do that, we know the base power, our system base power, this is the base power actually of the transformer. So when we do that calculation, we arrive at this. We do this, we look at motor. What is it for motor? We see also for motor that we are giving the per unit impedance of the transformer in base power of 50 AVA and base voltage of this. Now what we are trying to say here, this is actually not supposed to be transformer, this is for motor. Yes, so we notice that indeed there is a difference in base power. We also have difference in base voltage. So what do? We have that the base voltage for the load or the motor, for instance, we are given that the voltage for the motor is actually 13.8. Then whereas our system base, the one we have chosen, our new base, is actually 13.2. So you can see we had to convert the per unit value given to us for the motor to our new system base. Wow, having done this, we have arrived at all the per unit impedances for each of the components that was given to us in the power system. That is the generator, the transformer 1, the transmission line, the transformer 2, and the motor. Now we will now move to the next step. So what is the next step? The equivalent circuit. Wow. So this is where we have the equivalent circuit. So you can see this is for G1, generator 1, that is T1, for transformer 1, that is TL, for the transmission line, that is T2, for transformer 2, and this is the motor. So you can see finally this is the equivalent circuit. So from this now, depending on what we're asked, we can calculate all other parameters. Imagine you are given the voltage for this generator and say let the voltage be like we have here. We can say 1 pu. If you are told the voltage here is 1 pu, or you are told that the voltage here is 0.8 pu, if you have the voltage here to be 0.8 pu, of course we can calculate the current coming into this motor. How do we find the current? By dividing, using Ohm's law, dividing the voltage by what? The per unit impedance. And with that, we will now get the per unit current. And you know that because all these things are connected in series, you see the beauty of removing the transformer. If they are all connected in series, whatever the current coming here is the current passing also. With that, we can calculate the voltage drop here, we can get the voltage drop here, we can get the voltage drop here, and the rest of that. So this is simply how to also deal with a circuit of this nature. I want to believe that you have gathered some knowledge so far. So see you in our next class, and thank you for listening. Of course, we have an example we will want you to try. So this is it. So you can try your hand on this and see finally what you come out with. So thank you so much for listening, and make sure you try this example.